Have you ever wondered how your computer remembers your last action? This is not magic, but the result of a fundamental concept in computer science known as a stack. A stack is a special type of data structure that behaves in a last-in, first-out manner, often abbreviated as LIFO. Imagine a stack of plates or a pile of books. You can't easily remove a plate from the middle or the bottom of the stack, can you? Instead, you add and remove items from the top. This is how a stack operates in computer science. You add an element to the top of the stack, and when you need to remove an element, you take it off the top. The last item you put on the stack is the first one you take off. So in essence, a stack is a special type of data structure where the last element added is the first one to be removed. Now what can we do with a stack? Well, let's dive right into the 5 basic operations of a stack: push, pop, peek, isEmpty, and size. These operations are the heart of a stack's functionality. First up, we have the push operation. Picture a stack of books. When you add a book to the top, you're pushing it onto the stack. In the world of computer science, this is how we add an element to the top of our stack. Next, we have the pop operation. This is the opposite of push. If you take the top book off your stack of books, you're popping it off. In stack lingo, pop removes the top element from the stack. Now, imagine you want to see what book is on top of your stack without removing it. In stack terms, this is the peek operation. It allows you to retrieve the top element without removing it from the stack. Moving on, we have the isEmpty operation. Just as it sounds, this operation checks if the stack is empty. It's like looking at your book stack and realizing you've read them all. In programming, isEmpty returns a Boolean value, true if the stack is empty, false otherwise. Finally, we have the size operation. This operation returns the number of elements in the stack. It's like counting the number of books in your stack to see how much reading you have left. Now, why are these operations important? Well, they form the core of stack functionality. Whether it's managing function calls in your program, evaluating arithmetic expressions, or even implementing that handy undo feature in your text editor, these operations are at play. In essence, these operations govern how we interact with a stack. They let us add elements, remove them, check what's on top, see if the stack is empty, and determine how many elements are in the stack. These operations form the foundation of how a stack works and are essential to understand its applications. Okay, we know what a stack does, but how do we create one in a programming context? The answer lies in understanding that stacks can be implemented using various data structures. The most common choices are arrays and linked lists. Each has its own set of advantages and is suitable for different scenarios. Let's take a look at a simple implementation of a stack using an array in Python. We'll start by defining a class called stack. This class will have a constructor that initializes an empty list to store our stack's elements. We'll also add a few methods to our stack class. The first one is isEmpty. This method checks if the stack is empty by comparing the length of our items list to 0. If they match, it means that the stack is indeed empty. Next, we will add a method called push, which is used to add an element to the top of the stack. In the context of our list, this means appending the item to the end. Following that, we'll implement the pop method. This method removes the top element from the stack. But before doing that, it checks if the stack is empty. If it's not, it pops the last item from the list. If it is, it raises an index error, indicating that the stack is empty. We'll also need a method to retrieve the top element without removing it. We'll call this method peek. Like the pop method, it first checks if the stack is empty. If it's not, it returns the last item from the list. If it is, it raises an index error. Finally, we'll add a size method that returns the number of elements in the stack. This is simply the length of our items list. So there you have it. That's a basic implementation of a stack using an array in Python. It might seem simple, but it's a powerful tool that you'll find incredibly useful in various programming scenarios. And that's how you can implement a stack using an array in Python. So where do we use stacks in real-life scenarios? Well, one of the most common applications of stacks is in expression evaluation. Have you ever wondered how your calculator knows the order in which to perform operations when you type in an equation? It uses a stack to keep track of the operations. Stacks are used to evaluate arithmetic expressions, determining the order of operations based on precedence rules. They're also used to check for balanced parentheses in code or to convert infix expressions to postfix or prefix notation. Another area where stacks come into play is in function call management. In many programming languages, a call stack is used to manage function calls and return addresses during program execution. When a function is called, a new frame is pushed onto the stack, containing the function's local variables and return address. When the function finishes executing, its frame is popped from the stack, and control returns to the address at the top of the stack. This ensures that function calls are handled in a last-in, first-out manner, matching the behavior of a stack. But that's not all. Stacks are also handy when it comes to backtracking. Backtracking is a common algorithmic technique that involves exploring all possible solutions to a problem, and then backing up or undoing steps when a solution path proves unfruitful. This is seen in algorithms such as depth-first search, DFS, in graph traversal. Starting from a root, the algorithm explores as far as possible along each branch before retracting steps. This is where a stack comes in handy. It keeps track of the vertices of the graph. And last but certainly not least, stacks are used to implement undo mechanisms in text editors or other software applications. You know the relief you feel when you accidentally delete a chunk of text, but can bring it back with the undo function? Yep, you can thank stacks for that. Every time an operation is performed, it's pushed onto a stack. If the user decides to undo an action, the application simply pops the operation from the stack and reverses it. This is possible because stacks maintain the order of operations in a last-in, first-out manner. As you can see, stacks are quite versatile and find numerous applications in computer science and programming. But how efficient are stacks in terms of time complexity? That's a great question. Let's break down the time complexity of the basic stack operations: push, pop, peek, and isempty. When we talk about push and pop operations, they are blazingly fast. Adding an element to the top of the stack or removing it takes a constant amount of time, no matter the size of the stack. This is what we call O1 time complexity. Now, what about peek and isempty operations? Well, these operations are just as swift. Peeking at the top element or checking if the stack is empty also have a time complexity of O1. So regardless of the size of your stack, these operations will always take the same amount of time. This makes stacks incredibly efficient and reliable tools in your programming arsenal. So stacks are not only intuitive, but also offer efficient operations. Let's summarize what we've learned about stacks. A stack is a fundamental data structure in computer science, characterized by its last-in, first-out or LIFO behavior. This means that the last element added to the stack will be the first one to be removed. It's similar to a stack of plates or books where you can only add or remove items from the top. The basic operations of a stack include push, pop, peek, isempty, and size. Stacks can be implemented using various data structures, with arrays and linked lists being the most common choices. They find applications in various areas like expression evaluation, function call management, backtracking, and undo mechanisms. The time complexity of push, pop, peek, and isempty operations is typically O1. And that's a wrap on stacks, a simple yet powerful data structure that plays a crucial role in computer science and programming.